Right now, your body is fighting a war it will one day lose. Trillions of cells, constant repair, an immune system standing guard every second, whether you notice it or not. But the moment that war ends, something else begins. For 99% of human history, death happened in the open, in dirt, in water, in caves, in shallow graves dug by hand. Nature took the body back on its own terms. No chemicals, no caskets, no delay. Today, most of us will never see what that actually looks like. So, what really happens to your body over the next 100 years? Not the version in movies. Not the sanitized version funeral homes prefer you not to think about. The real biological, chemical, and geological process, mapped out stage by stage, year by year, decade by decade. You might think death is an ending. It's actually a handoff. The moment your heart stops, your body doesn't shut down all at once. It shuts down in stages, and some of those stages are stranger than fiction. Within minutes, oxygen stops reaching your cells. Without oxygen, your cells can't produce the energy they need to keep functioning, so they start breaking down from the inside. This is called autolysis, which just means self-digestion. Enzymes that used to help you break down your lunch now start breaking down you. Blood stops circulating and begins to pool wherever gravity pulls it, usually toward your back if you're lying face up. Within a few hours, this creates dark purplish blotches on the skin called livor mortis. Forensic investigators use this pattern to figure out whether a body has been moved after death, because the blood settles in a very specific, predictable way, and any bruise-like marks in the wrong place can reveal a body was repositioned. At the same time, your muscles begin to stiffen. Calcium floods into muscle fibers and locks them in place, causing rigor mortis, that familiar stiffness people associate with death. It usually peaks around 12 hours after death, and then, strangely, fades again after about a day or two, as the muscle tissue itself starts to break down. This is where most people's understanding of death stops. But this is only the first 48 hours. Here's where the story gets interesting. You are not sterile. You never have been. Your gut alone contains trillions of bacteria, an entire ecosystem your body kept in careful balance while you were alive. Once your immune system goes offline, that balance collapses, and those bacteria don't die with you. They start eating. This process is called putrefaction, and it's driven largely by anaerobic bacteria already living inside your digestive tract. They begin consuming your tissues from the inside out, producing gases as a byproduct: methane, hydrogen sulfide, and other compounds that build up inside the body because they have nowhere to go. This is why bodies bloat. The abdomen swells first, sometimes dramatically, as these gases accumulate with no way to escape. It's also why decomposing bodies can seem to shift position slightly, gas escaping the lungs or moving through soft tissue. There's no ghost involved, just chemistry doing what chemistry does. Forensic anthropologist William Bass understood this better than almost anyone alive. In 1981, at the University of Tennessee, he founded what's now informally known as the Body Farm, a research facility where donated human bodies are placed outdoors under varying conditions specifically to study decomposition scientifically, rather than guessing at it. Before Bass's facility existed, much of what forensic scientists knew about decomposition timelines came from animal studies, pigs mostly, which turned out to be a flawed stand-in for human tissue in several important ways, since body fat distribution, gut bacteria, and skin thickness all differ. Bass's research and the decades of forensic taphonomy that followed it revealed that decomposition isn't a single fixed timeline. It shifts dramatically based on temperature, humidity, soil chemistry, oxygen exposure, and whether insects can reach the body. A body in a hot, humid climate can skeletonize in a matter of weeks. A body in cold, dry conditions can remain largely intact for years. Insects, it turns out, are one of the most reliable clocks scientists have. Blowflies are usually the first responders, arriving within minutes of death in outdoor conditions, drawn by the smell of decomposition gases long before humans could ever detect them. They lay eggs, usually in moist areas like the eyes, nose, and mouth. Those eggs hatch into maggots within about 24 hours, and the maggots begin feeding. This might sound unsettling, but maggot activity is actually one of the most useful tools in forensic science. Because insects colonize a body in a very specific, predictable sequence, first blowflies, then flesh flies, then beetles. Entomologists can examine which species are present and how developed they are to estimate, sometimes down to the day, how long a person has been dead. This field even has a name, forensic entomology, and it has helped solve criminal cases that would otherwise have gone cold. So what does your body look like after, say, 1 month? By this point, if your body was left exposed to open air, soft tissue has largely broken down. Skin darkens and eventually sloughs away. Internal organs, the ones richest in bacteria and moisture, tend to liquefy first, particularly the digestive tract, liver, and brain. Denser tissues, like tendons, ligaments, and cartilage, resist much longer, sometimes persisting for months after everything else is gone. At around 1 year, in typical temperate conditions, most soft tissue is gone. What often remains is bone, cartilage, hair, and sometimes patches of leathery skin that have dried out faster than they could decompose, a process called mummification. This isn't the wrapped, embalmed mummification of ancient Egypt. It's a natural process that happens anywhere. Conditions are dry enough and airflow good enough that bacteria can't break the tissue down before it dehydrates past the point bacteria can use it. Now picture something stranger. If a body ends up in wet, oxygen-poor conditions instead, cold water, waterlogged soil, or an airtight environment, something else can happen. The fat in the body can undergo a chemical transformation called saponification, converting into a waxy, soap-like substance called adipocere. Sometimes called grave wax, adipocere can preserve the general shape of a body, sometimes even facial features, for decades, occasionally for over a century, long after the bones beneath it would otherwise have been picked clean. This is exactly what happened to Europe's famous bog bodies. Bodies like Tollund Man, discovered in a Danish peat bog in 1950, are so well preserved by the bog's acidic, low-oxygen, tannin-rich water that his facial expression, the stubble on his chin, even the rope still around his neck, were clearly visible over 2,000 years after his death. Peat bogs act almost like a natural embalming chamber, halting bacterial activity almost entirely while slowly tanning the skin like leather. A process researchers studying bog chemistry have linked to the sphagnum moss itself, which releases compounds that bind and preserve organic tissue. Bury a body 6 feet under in an ordinary cemetery, though, and you get a completely different 100-year story, one shaped as much by geology as by biology. Let's reconstruct it, decade by decade. Year 1, assuming no embalming and a simple wooden or biodegradable casket, soft tissue decomposition continues underground, just slower than on the surface, since soil temperatures are cooler and oxygen is limited. Anaerobic bacteria dominate here instead of the oxygen-loving species active above ground, so the process, while still active, is quieter and slower, without the bloating and insect activity you'd see on the surface. Years 1 through 10. The casket, if wooden, begins to break down. Wood is organic material too, and soil fungi and insects treat it the same way they'd treat a fallen tree. As the casket loses structural integrity, the earth above it settles, which is part of why older cemeteries often show gently sunken patches of ground above graves, sometimes decades after burial. Soft tissue is essentially gone by this stage in most soil conditions. What's left is skeleton, some cartilage, hair, and nails, which are made of keratin, a tough structural protein that resists bacterial breakdown far longer than muscle or organ tissue does. Years 10 through 50, bone itself starts a much slower transformation. Bone isn't inert. It's a living, mineralized tissue made mostly of collagen and calcium phosphate. After death, groundwater slowly leaches organic material out of the bone matrix, collagen breaks down, and the bone becomes increasingly brittle and porous. In acidic soils, this process accelerates. In alkaline, dry, or very cold environments, it can slow to a crawl. This is precisely why archaeologists find skeletons that are thousands of years old in some regions of the world, while in other soil types, bones from just a century or two ago have crumbled to fragments. Years 50 through 100. This is where the timeline becomes highly variable, and honestly, where most people's assumptions about dust to dust start to break down, pun very much intended. In favorable conditions, deep burial, stable temperature, limited groundwater flow, dense mineralized bone can persist essentially intact for well over a century. Teeth, which are even more mineral dense than bone, often outlast every other part of the human body by a wide margin. Dental enamel is the hardest substance the human body produces, harder than bone, and it's frequently the last recognizable human structure to disappear from an old gravesite, which is why archaeologists so often identify ancient remains by their teeth alone. Anthropologist and taphonomy researcher William Bass wasn't alone in mapping this out. Forensic chemist Arpad Vass, working at Oak Ridge National Laboratory, alongside data gathered from the body farm, spent years cataloging the specific chemical compounds released during human decomposition, identifying hundreds of distinct compounds that make up what researchers sometimes call the smell of death. His work helped train cadaver dogs with far greater precision and gave forensic investigators chemical markers to help estimate time since death, even when a body has fully skeletonized, using something he called a decomposition odor profile. There's also anthropologist Kathy Reichs, whose forensic casework and academic research on skeletal trauma and identification have shaped how investigators read bones for clues about age, sex, and time since death. Work that has quietly influenced how museums and universities catalog centuries-old remains today. Here's the twist most people don't expect. We tend to picture decomposition as total, complete erasure. Ashes to ashes, nothing left. But under the right conditions, nothing left can take thousands of years, not 100. Skeletal remains from Ice Age burial sites, tens of thousands of years old, have been recovered essentially intact, teeth included, because the surrounding environment happened to be cold, dry, or mineral stable enough to preserve them. Meanwhile, a body embalmed in a sealed steel casket inside a concrete burial vault, the modern standard in many places, can actually decompose more slowly and unpredictably than a body buried simply in a shroud, straight into soil. Sealed environments trap moisture, which paradoxically can encourage certain kinds of bacterial breakdown once the seal eventually fails, sometimes producing decomposition that looks more advanced, not less, than a body given no barrier at all. Nature, it turns out, is often more efficient at handling a body than we are. Let's reconstruct one specific grave, the way an archaeologist might approach it after unearthing it a century later. Picture a modest cemetery plot from roughly 100 years ago. No concrete vault, just a wooden coffin, common practice at the time. The excavation team brushes back soil layer by layer, the way sediment itself recorded the passage of time. Near the surface, root systems have woven through the upper layers. Tree roots often follow the path of least resistance downward, sometimes growing directly through decayed coffin wood in search of the nutrient-rich soil a body leaves behind. This is one of the quiet ways human remains genuinely do become part of new growth, not poetically, but mechanically, through root uptake of decomposed organic material. Deeper down, the coffin's iron hardware, hinges, handles, nails, has often outlasted the wood itself, since metal corrodes far more slowly than cellulose breaks down. Archaeologists frequently find a rough coffin-shaped outline of rusted metal fragments long after the wood has vanished entirely, a ghost image of the object rather than the object itself. The skeleton, if conditions were reasonably dry, is often found largely in anatomical order, meaning the bones are still roughly where they'd be in a living body, held loosely in place by the last remnants of ligament, and by the simple fact that nothing has disturbed them. Smaller bones, the fine bones of the hands and feet, are the ones most often missing or scattered. They're small enough to shift with groundwater movement, be carried off by burrowing animals, or simply decompose faster due to their high surface area to volume ratio. The skull, meanwhile, tends to survive remarkably well. It's dense, thick in places, and protected somewhat by its shape. Forensic and archaeological teams often rely on the skull specifically for identification, since features like the eye sockets, brow ridge, and jaw structure preserve information about a person's characteristics long after soft tissue is gone. This is what 100 years actually tends to look like underground. Not a body, and not nothing. Something in between. A skeleton, incomplete but recognizable, embedded in soil that has quietly absorbed the rest of what that body used to be. Cremation tells a different story entirely, and it's worth understanding by contrast. Modern cremation exposes a body to temperatures around 1400 to 1800 degrees Fahrenheit for 1 to 3 hours, which combusts soft tissue almost entirely and leaves behind brittle bone fragments, not ash in the traditional sense. Those fragments are then mechanically processed into the fine, uniform texture people recognize as cremated remains. Chemically, what's left is mostly calcium phosphate, the same mineral compound that makes up bone in the ground, just concentrated, dried, and inert. Scattered or buried, those minerals are remarkably stable. Unlike a buried skeleton, which keeps slowly interacting with its environment for decades, cremated remains have already finished almost all of their chemical transformation before they ever touch soil again. Let's zoom out, because there's a bigger pattern here. Every material your body is made of already has a natural waiting room it belongs to. Water returns to groundwater. Carbon returns to soil and eventually to the atmosphere, cycled by microbes and plants. Calcium and phosphate, locked in your bones, slowly rejoin the mineral cycle of the earth. The same cycle that built those minerals into rock millions of years before you were ever born, and will keep cycling them long after. Nothing about this 100-year process is unusual by nature's standards. What's unusual is how rarely we watch it happen. This is the part that should genuinely change how you think about death. For nearly all of human history, this entire process was visible. Grief and biology sat next to each other. People washed the bodies of their own dead, buried them by hand, and watched across seasons as the earth reclaimed what it was owed. Death wasn't hidden behind hospital walls and refrigerated drawers. It was a process people understood intimately because they participated in it directly. The way earlier ancestors understood birth, illness, and hunger through firsthand contact rather than abstraction. Modern life has pushed nearly all of that out of view. Embalming, refrigeration, and sealed caskets aren't really about preservation in any biological sense. Decomposition still happens eventually, just delayed and often distorted. They're about distance, about not having to look directly at the thing every human body before ours eventually became. And maybe that distance is exactly what makes death feel so unfamiliar now. Something to fear in the abstract, rather than something to understand as a continuation of a process your body has been running quietly your entire life. Autolysis, cell turnover, bacterial balance. Your body was never a fixed, permanent object, even while you were alive. It was always mid-process. Death simply changes which direction that process runs. Anthropologists studying ancient burial practices have found something remarkable when they compare cultures separated by thousands of miles and thousands of years. An overwhelming number of them independently arrived at burial practices that, whether they understood the microbiology or not, actually slowed decomposition or preserved remains in some intentional way. Egyptian embalming used natron, a naturally occurring salt mixture, to dehydrate tissue and halt bacterial activity, essentially engineering the same dry preservation conditions that occur naturally in a desert grave. Andean cultures in the pre-Columbian era buried some of their dead in high-altitude, cold, arid conditions that mummified bodies naturally, without any chemical intervention at all, simply by taking advantage of an environment bacteria couldn't thrive in. Archaeologist Johann Reinhard, known for his high-altitude research in the Andes, documented remarkably preserved remains found near mountain summits, preserved for centuries by cold and low humidity alone, not embalming. None of these cultures had microscopes. None of them understood bacteria, enzymes, or anaerobic decomposition in the terms we use today. But they observed, generation after generation, which burial conditions worked, which ones kept a body recognizable, and which ones didn't. And they built traditions around those observations long before anyone could explain why they worked. That's worth sitting with for a second. The science you just learned, autolysis, putrefaction, adipocere, mineralization, isn't new information humans stumbled onto recently. It's the explanation underneath practices people were already quietly getting right, purely through generations of careful observation. Think about your own body for a second. Right now, skin cells you had a month ago are already gone, replaced by new ones. The lining of your gut renews itself every few days. Even your bones, the part of you that will likely outlast everything else, are constantly being broken down and rebuilt by specialized cells your entire life. You have never, at any point, been a finished object. You've always been a process wearing the appearance of a fixed thing. Death doesn't interrupt that. It just removes the maintenance crew. 100 years from now, if your body is buried simply in the ground without a sealed vault, chances are your skeleton is still there, slowly demineralizing, slowly returning its calcium and phosphate to the soil that will eventually become part of a tree or a blade of grass or the next thing that grows there. Not metaphorically, literally, the same atoms. This is also why so many forensic scientists describe their work not as something morbid, but as something almost tender. Every stage of decomposition follows rules. Every clue a body leaves behind, insect activity, soil chemistry, bone density, tells a story that can be read, understood, sometimes even used to bring a missing person's name back to their family. Researchers who spend their careers at facilities like the Body Farm often describe an odd shift that happens the longer they study death professionally. The fear fades, and what's left is closer to respect. Respect for how consistent the process is. Respect for how much information a body can still communicate long after the person inside it is gone. It's worth asking why this topic feels taboo at all. Every single human who has ever lived has gone through exactly this process, or one very much like it. There is no exception. No wealth, no status, no technology has ever fully escaped it, only delayed it, sometimes by decades, never permanently. And yet most people will go their entire lives without learning even the basic outline of what their own body will do after they're gone. Compare that to how ancient humans lived. Death wasn't an abstraction reserved for hospital paperwork and hushed conversations. It happened at home, among family, often within view of the people who loved that person most. Children in most pre-industrial societies grew up understanding, at a basic level, what a body looked like at every stage after death, because they were present for burials, present for mourning rituals, present for the physical, undeniable reality of it. That closeness didn't make death less painful. Grief is grief, in any century, but it did make death less mysterious, less frightening in the abstract sense that so many people carry with them today. Somewhere along the way, especially over the last 100 years or so, industrialized society built an entire infrastructure specifically designed to keep that process out of sight. Funeral homes, refrigerated morgues, embalming chemicals, sealed caskets. None of these actually stop decomposition. They only pause it, reroute it, or delay its visibility until after a viewing is over and the casket is sealed for good. In some ways, modern death has become less about biology and more about staging, a final appearance managed as carefully as any other part of modern life. But underneath all of that staging, the same ancient process is still running exactly the way it always has. Autolysis still happens. Bacteria still take over. Insects still colonize a body wherever they can reach it. Bone still slowly gives its minerals back to the earth. No amount of modern intervention changes the underlying chemistry. It only changes how long you can avoid looking at it. You spend your whole life thinking of your body as something that belongs entirely to you. For 99% of human history, and for the 100 years after everyone who has ever lived, it eventually belongs to something much bigger.